Okay, so let's do some more work with electric fields. Here we've got a field of 760,000 newtons per coulomb, and inside we have a copper nucleus. So first things first, I need the mass and charge of my copper nucleus, and we're using copper, and we're using copper 6429. So we've looked at this a little bit already, and there's other videos on that are on your YouTube channel to remind you how to do this type of thing. But we've got the atomic mass of 64, the atomic number of 29. So we can use the atomic mass to find out what the mass of the nucleus, and then we can find use the atomic number of 29 to find the charge of the nucleus with the 29 protons. So if we do this, we can get the mass would be around 1.07 times 10 to the negative 25 kilograms. And the charge of the nucleus would be 4.64 times 10 to the negative 18 coulombs. All right, so there's the mass and the charge. And what we're going to do is we're going to see if we can find out, let's just see if we can find out what's the acceleration of the nucleus inside that field. Okay, well, I've done this type of thing before, and of course you've got the electric field and you've got the charge. So you could do F equals QE, or we had a capital Q, so F equals QE to find the force. And then once you have the force, the acceleration would just be the force divided by mass. Well, let's see if we sort of start putting a couple of things here together. It's really common for people to start combining expressions, and instead of doing two calculations, you can sort of do it in one, where the acceleration would just be QE divided by m, where this part up here, that is just the force right there. That's just your electric force. So the acceleration would just be QE over m, or force divided by m. It's just a little bit quicker, a little less rounding and stuff like that, so your answers can be a little more accurate, and it works out pretty well. So we've got the charge. We found that in coulombs. That's that 4.64 to the power of negative 18. That is our charge. We multiply that by the E of 760,000 newtons per coulomb, which would give us our force, which is around 3.5 to negative 12. And then we'll divide that by the mass that we found right away, the 1.07, so the power of negative 25. And then we've got our acceleration, which will be around 3.3 to the power of 13 meters per second squared. So there's the acceleration of the nucleus as it goes across. And then, of course, you could find the distance and times and other things as well, possibly. But we're just looking for the acceleration right now. Okay, so let's try a different question here as well. Okay, so in this question, we have a negative charge between a couple plates, and the charge apparently is 5.6 to the negative 18 kilograms, and negative 3.2 to the negative 7 coulombs. And the plates are 825 micrometers apart, and it goes across in 4.2 nanoseconds, and we're looking for the electric field. Well, first things first, I'm going to draw my electric field. Now, this is a negative charge, which means if my negative charge is going towards the right, my electric field must be going towards the left, because negative charges will always go against the field. The other way I can think about it is the plate on the right must be positive in order for the negative charge to want to go towards it. And if this is the positive plate, this would have to be the negative plate, and electric fields go from positive to negative. So that's another way I know it's going to the left. Okay, well, let's see what else I can find now with information that I'm given. Well, first of all, I've got distance and time, and distance and time will give me my average V. So careful with the prefixes. You got the negative 6 with the micro, you got the negative 9 with the nano. So we'll divide those two out, and we can get the average speed of our charge, which should be around 1.96 times 10 to the 5 meters per second. And if that was the average V, and it'll go, start at 0, and it'll hit the other plate at maximum speed, all we have to do is double it, and we'd have the change in V for our little charged objects, which would be around 3.93 times 10 to the 5 meters per second. So there are my V's. Well, I can keep on going with this because, of course, with change in V and time, I can find acceleration. because acceleration is change in v over change in t. So I got the 3.9, I've got the 4.2 nanoseconds. So divide those two out, get an acceleration of around 9.36 times 10 to the 13 meters per second squared. Okay, now that I have that, I should have everything I need to find my electric field, because electric field is going to be force divided by charge, and of course the force would just be ma, and I have my q value already. So I've got my mass, that's over here, I've got my acceleration, that's over here, I've got my q, that's over there. So multiply the top out and divide it by the q, and I will get an electric field around 1640 newtons per coulomb. Now the thing is, when you do the calculation, technically that q is negative and technically the acceleration is negative, but they'll end up canceling out as well. So you just end up with the electric field of 1640, and I know that it's going towards the left because the negative charge would go the opposite direction that the field is actually going. Okay, so there's my electric field, 1640 towards the left. Okay, all right, let's try another question as well. Okay, so for this one, we got a charge inside 1400 newtons per coulomb. It goes across the plates, which are 7.5 millimeters apart and 0.142 nanoseconds. And it's got a charge of 8.35 to the negative 8 coulombs. And this time we're looking for the mass. Okay, well, just first things first, let's see what we can find. Once again, we got distance and we got time, so we can calculate our average v. We've done this before. So if we do our distance divided by time, get around 5.28 times 10 to the 7 meters per second. And again, we'll double that. And our change in v would, of course, be twice this. So for our change in v, we're looking at around 10.6 times 10 to the 7 meters per second. Okay, well, we've got change in v like we've done before with change in v, and we've also got the time over there. We can find our acceleration. So acceleration would be the change in v over change in t. There's our change in v. There's our change in t. So we'll divide the two out, and you'll get 7.44 times 10 to the 17 meters per second squared. Okay, so we got the acceleration. Well, next is just basically we can take the forces, where QE equals MA, the two forces things. Same as this one up here, except we're going to rearrange for mass instead. And of course, the mass would be equal to the electrical force divided by the acceleration. You got the Q, you have the E, we found the acceleration, so we multiply and divide things out, and we'll get a mass of about 1.57 times 10 to the negative 22 kilograms. So again, more basic DTV, VAT, F equals MA, similar type of stuff. Okay, so that's how we can do that one. All right, well, let's try another question. Okay, for this one, here we have an alpha particle between two plates that are 0.42 micrometers apart, and it hits the other side going 0.72 C. Now, we've done this type of thing before, where it's doing 0.72 times the speed of light, so we've got to convert that to meters per second. So this would be 2.16 times 10 to the 8 meters per second. That's going to come in handy, and of course this will be our change in V. So of course we could just cut that in half to get our average V. So our average V would just be half of that. So 1.08 times 10 to the 8 meters per second, and that could come in handy. The other thing, of course, is an alpha particle. We've mentioned this before. An alpha particle is just a helium nucleus. So if it is helium, it's basically helium-42. I need the mass and I need the charge of a helium nucleus. So we've done this type of thing before, and if we can do the conversions, we've got the atomic mass of 4 times the atomic mass unit. We've got a mass of 6.68 times 10 to the negative 27 kilograms, and we've got a charge of 3.2 to the negative 19 coulombs. So there is our helium nucleus. All right, so what we're going to do now that I just found some stuff that just sort of popped into my head just by looking at the question with the C calculation. I know I need the different value for the speed. It's a helium nucleus. I know I'm probably going to need the mass and charge, so I'll get that out of the way. Now for the actual question, we are going to find the electric field. Okay, so to find the electric field, we've got the mass, we've got the charge, we will need the acceleration, and we can find the acceleration by using our basic V quantities and piecing things together. So I've got distance and I've got average V. We've done this type of thing before. So the time to get across would be the distance divided by the average V. So if we do that, it should take approximately 3.89 times 10 to the negative 15 seconds for it to get across. Once I've got that, I've got my change in V and my time. I can find my acceleration. So acceleration will be change in V divided by time. So I can find my acceleration, which is around 5.55 times 10 to the 22 meters per second squared. And then once I got that, electric field, relatively straightforward. Electric field is going to be the MA divided by the Q. Mass I've got right there. Acceleration I've got right there. Q I've got right there. So I can punch them all out and I can solve for my electric field, and I should get around 1.16 times 10 to the 15 newtons per coulomb. Okay, so we've done a few questions like this already, and hopefully you're starting to see it's the same thing over and over and over and over again. Similar calculations. Again, the prefixes and different types of values you have to use a little bit different, but the majority of the steps in the calculations are very similar to what you guys have done previously.